So for the sake of maybe somebody new or just to get started, let's recall where we stopped. I hope I remember where I stopped. I tried to look at the last lecture video, but I didn't get the time. I just made it in. I came here at 4 o'clock, but Professor Jamadani called me for another meeting, and I escaped from there and came now. Okay. So we first introduced construction of real numbers. We were in the chapter on real numbers. So construction of real numbers. This was done in two different ways. We used Cauchy sequences, okay, through Cauchy sequences and equivalence classes and so on and so forth. Basically, I think it was done by Cantor, and Cantor probably called them fundamental sequences. He didn't use the word Cauchy sequences. And then we also introduced the Dedekind cuts through Dedekind cuts, and of course there is a theorem which says both constructions are isomorphic, okay, with all aspects, everything, the algebra, the arithmetic, everything can be translated from one to the other, so both get essentially the same construction. And after that we started discussing the fundamental topological properties of the real line. So from now on I denote the real line by R. Okay, I will talk to this later. Now in this, the main thing that is observed was that for every real number R, we associate what is known as its absolute value, mod R, which is R, if R is positive. Of course, when we constructed, we had everything including the order, okay. So greater than everything was there, minus R if R is less than 0, and 0 if R is equal to 0. And this was the starting point, and this gives rise to the fact that if R and S are real numbers, we can define the distance between R and S. We don't care which direction move, actually the absolute value of the difference between R and S. This probably is the seed that gives the topology for the real line. The entire topology of the real line generates, the usual topology generates from this particular seed, okay. Then we introduce the fundamental thing that if the word topology comes from topography, okay, the study of neighborhoods. So if I have a point, if I have a real number A, we look at all the points which are within a distance of epsilon, or let me put, okay, if epsilon is any positive number, okay, from now on, okay. This is, so given A in R, then for epsilon positive, the set all x in R such that they are within a distance epsilon from A. This is just the distance AX. Within a distance of epsilon is called, we will denote it by the interval of radius epsilon centered at A, okay, by epsilon A. This is called the epsilon neighborhood of that is like in the current, if you look at the controversies BBMP going on, you make sure you don't go right up to the radical or drainage or anything like that. So you take a small neighborhood and be happy with it, okay. So we'll make epsilon as small as possible if you want. So any such epsilon is called the such a set is called, the set of all points within a short distance from that point A is called an epsilon neighborhood of A. These are common sense definitions, very old. Now, again we want to make sure that whether we are, when we are taking an epsilon neighborhood of A, we are in a sense, in some sense, encroaching upon somebody else's territory. Okay, so that we want to avoid. So suppose we are given, so let S be a subset of R, and then we have a point A in S. Then we look at, so now we are looking at all the points in R who are close to A, but some points may be out of that set S. Okay, so the S is only a subset of A, R, and we are looking at all points X in R which are within a distance A. When I take all points which are within a distance of A, some of these points may be out of the set. So you are encroaching upon somebody else's territory. So we want to look at all those safe points. What are the safe points for which at least some neighborhood is there, such that which consists of all the points only from the set S. So A belonging to A such that there exists an epsilon positive, this whole thing is contained in S, no encroachment. Okay, such a point is called an interior point of the set, is called an interior point of the set. So we look at all safe points where you can construct, okay, so that the BMP doesn't come and disturb us, okay, and we will denote by S superscript 0 O the set of all A in S such that A is an interior point of S. This is called the interior of S. And clearly, because the interior consists of points in S with some special property, so clearly the most dangerous word when you, all the interior points are also in S. We are looking at the interior points of S. They are all points of S with some additional property. So they may be all of S, but some of them may not be interior points, in which case S may be bigger. Okay. Now comes the case where you have brought a clean site, that is your set S is such that the interior is exactly equal to S. So no encroachment for in any part of your house. A set is said to open set if S naught is yes. That is, every point is an interior point. That is, every point of S is an interior point. What does that mean? That is, for every S in S, there exists epsilon positive such that I epsilon S is completely contained in S. Okay. That's what is meant by an open set. Okay. This is all done before, so I am just recollecting all the definitions. If you want to listen to it, I mean, it's all, I think the videos are posted, so it must be in the last 2 lectures or the last lecture the video is posted. Okay, I don't know what notations I used. The collection of all these open sets gives you what is known as the neighborhood sets of the real line. So we say, I think I might have used script O, okay, the collection of all open sets we will be looking at several collections of sets, okay, in the real line with various characterizations which bring out many things, okay, and there will always be some things connecting with the various types of sets. Some of the things that we observed, well, recall again. We had the following properties of the open sets, namely that are both open sets. The empty set and the real line are both open sets. And the open sets were nicely close with respect to unions. That is, A alpha is any collection in Wu. When I say any collection, it may be finite, it may be a sequence, or it may be uncountably infinite also. Then their union is also an open set. Okay, we will come to this point. Then, however, we can't say that when you come to intersection, you can't take any collection, you can take only finite collection. I mean, that is the only thing that is assured. Aj, j equal to 1 to n, finite collection in O, open sets implies intersection Aj, j equal to 1 to n is also an open set. So the dual of this is the closed sets. Take everything the complementary side. Okay, if I will say something is a closed set, if its complement is a open set. So that's the next thing that we say F contained in R is called a closed set if F complement is an open set. And therefore the dual results must be available. So if this is open, its complement must be closed, that is this must be closed. If this is open, its complement must be closed. So phi and R are both, so phi and R are both. Okay, let me denote by capital F, script F, the collection of all closed sets. So the first property we get from there is phi complement R and R complement are closed sets. And the dual of this is the intersection of any collection of closed sets will be closed and the union of a finite collection of closed sets will be closed. So A alpha, any collection belongs to F implies intersection alpha, A alpha belongs to F, and Aj, j equal to 1 to n is a closed set implies union j equal to 1 to n, Aj is a closed set. Okay, so these are simple properties of open and closed sets that we had proved, observed and all. Okay, one of the great activities in classical analysis was building. Starts from some very nice things and try to build more complex things out of them. Okay, so let's say the simplest thing I started with was the neighborhood, open interval. Okay, so let us even call how do I call it? OI to be the collection of all. Among the open sets, I am looking at only open intervals. This is not standard notation. This is something I just thought about now only. Okay, the collection of all open intervals. I am not going to look at all open sets, but in those collection of open sets, I am taking special fellows who are just open intervals. Okay. Now, what can I build out of them? Now when I say build, how do I build? The only thing that I can do with sets is do set theoretic operator, put the union, intersection or whatever I want to do, and then I can build. Okay. So particularly if I put unions, what will happen? If I put a number of open intervals, well, the one thing I get, maybe there is not an interval. For example, I can take an interval 0, 1 and another interval 3, 10. When I put the union, I am not going to get an open interval, but I will get an open set because each is an open set and the union of open sets is open set. So when if I try to put two open intervals together, I get a open set. If I try to put many open intervals together, I still get only open sets because union of open sets is open. So therefore, we can put together I mean take the union. Any number of open intervals will get open sets, really. Okay, but is the converse true? Can I build all open sets like this? In other words, given an open set, can I express it as the union of open intervals? The answer is obviously yes. Okay, let me put it this way. Okay, first put the question. Question: can I get all open sets by this process? So what do you mean? That is, given any open set G, okay, I don't know why. Actually, the G was a very common notation for open sets. That was denoted by script G, and this is denoted by small g because G is the first letter, first alphabet for the word for open in German. Okay, so G was used almost in all old textbooks for open sets, and old timers like me always use G. Given any open set G, all this in R. Okay, can we express it as a union of open intervals? When I say a union, I can put any union. It can be finite, countable or uncountable infinite because that is allowed to still you will get only open sets. The answer is obviously yes. The answer is obviously yes. So whenever an analyst or in particular and a mathematician in general says obviously yes, it means there may be a few lines that you will have to write, and I am lazy to write that, that's all. So what it means is the following. So why is that true? So G is given. Take any point A in G. Because G is an open set, there must be a neighborhood of A which is in G, implies there exists epsilon positive such that I epsilon A belongs to G. Let us call this as a set GA. Okay, a GA which completely belongs to G, and A is a part of GA, A is inside GA. Now take the union of all the GAs, GA is open because it is an open interval. Take GA and take the union of all the GAs and vary A over G. Corresponding to every point you have a GA, you take all the union. Now since every one of them is in G, the whole union is also in G, because every GA is contained in G. On the contrary, this contains G because every element of G is in one of the GAs. If you take an element of G, it is one of the GG. Suppose you take a G in G, it belongs to GG and therefore it belongs to the union because any A belonging to G is in GA and therefore the union GA belongs to G. So therefore the union A belonging to G, GA is equal to G. And therefore I express an open, this is a very trivial argument, okay, just in the beginning I will write all these things. So therefore every open set can be expressed as the union of intervals. So basically intervals are the interesting things because everything else, all these open fellows can be built. And now there is a finer result of this in the real life. Suppose I take an open set which has a huge number of elements, an uncountable number of elements, then I will have to take an uncountable union here. Okay, so whenever I want to do building process, the simplest building process is putting finite number of things together. Okay. And while this world real numbers being so big, uncountably infinite, to expect that we will do everything with only finite process is somewhat ridiculous, okay, unreasonable also. So therefore, what we should expect is, okay, I will allow a little bit of infinity, the smallest infinity. What is the smallest infinity? The countable infinity. So can you write this union as either a finite union or a union of a sequence of open sets? So a more refined question is, can we do better? The answer to this question was yes. Yes, I can express every open set as the union of open intervals, but can I do better? That is, can I express every open set as the union of a finite or a sequence of open intervals? That is what is a countable union of open intervals. The answer is yes, you can do it. Then we become a greedy, right? So in the answer is going to be yes. Then we become greedy and ask, well, maybe you are taking an interval like this, another time taking an interval like this, there is so much of redundancy. So can you express them as a disjoint union of a sequence of open intervals? So every piece must be disjoint. Okay, the question clear? And the answer is yes. That is a very famous theorem called the Lindeloff theorem. I think that's almost of the level at which my memory is that I finished when I stopped, that was where I was, okay. So let me recall this. So can we do better? So let me write all this up so that, can we do better? That is, given any G open set, can we express it as a union of either, I will write it, a finite number or a sequence or an infinite sequence of, that is simply, this whole statement is written in one sentence, countable union, a countable number of open intervals. And if so, can we make these open intervals disjoint so that completely the open set has been broken into pieces so that each piece is an interval, each piece is an open interval, and each piece is independent of the other fellow, and there are only finite number of them or a countable number of them. So that is a way of breaking up a open set into small standard pieces or putting all standard pieces to get a open set. This is the construction part. And the answer is yes, and the theorem is called the Lindeloff theorem. Lindeloff. The spelling I am never sure. But even if you see in an English book, it will be some one L or double L or whatever it is, with enough. But even that's wrong because the Russians will end it with a OV. Okay, that is pros, I think. Let me try whether my memory is correct. That's the name. Okay. So nobody knows Russian, I assume, so I can write anything I want. That's how the Russians write. It's Lindeloff. Okay. The H is an N, and the BI is E. This is L. And distorted pi is L, and the D is a little bit distorted written. E is E, O is O, and the ending. This is actually a V, but it has to be pronounced as F when it is coming in the end. This is like the name like Johnson, okay, something like that. What does Johnson? How did the name Johnson come? Son of John. This is of Lindell. This is son of Lindell. Okay, that's why it's Lindeloff. So Khrushchev was son of Khrushchev. That's all. Khrushchev is Khrushchevsky or something like that. Anyway, that's different. So it doesn't matter what spelling we write in English, it will not give the correct spelling. The Lindeloff theorem is every open set in R. I'm not going to prove this. To prove this, we need to do something more, which I have not yet done. But as a matter of discussion, I'm going to can be expressed as a countable union of disjoint open intervals. Okay, this is a very important theorem. Okay, and many proofs can be given using this theorem on the real line functions. Okay. So I was looking at the constructions, like what I can build. If I start with intervals, I try to put any number of intervals together and take their union, I will move up to open sets. Okay. So now I take this as my new arsenal. So now I have got open set. From open sets, I built up little more things familiar to me. Namely, I have got a whole collection of sets called open sets. Now, what can I build from them? Then I'll say, okay, put open sets together. Well, if I put open sets together, what do I get? Union of open sets is still open, nothing is got. Okay, so you are not going to get any more new variety of species from open sets by just putting open sets together. In other words, union stops there. Union doesn't take you any more beyond the construction of open sets. But then, if I intersect, I say, okay, let me try intersection. If I now take open sets and intersect two open sets, again nothing new I get, because the intersection of finite number of open sets is again a open set. So therefore, putting finite number doesn't get you anywhere. And I said, whenever construction with finite doesn't lead you anywhere, the best I allow you is to go to a countable number of them. See, I am very uncomfortable with, generally the construction wants to be at a sequential level, okay. I have to allow infinity, I will allow the least infinity that is allowed. So if I now take a countable number of open sets and I intersect them, then it will no longer be an open set, need not be an open set. You are likely to get something different. Okay, so whenever somebody new is born, you have to give a name for them. Okay, so we now call, so now you see, let's see, so next step of construction. Next step of building. Union of open sets gets us only open sets. Finite intersection of open sets, eventually we'll get to some sets which are very familiar and is a bugbear many times if you have not seen them. Open set gets us only to open sets. But intersection of a countable number of open sets may or may not be a open set. So we are, this process of intersecting a countable number of open sets is something that's going to be new. So we give a name. So a set, a subset S of R is called a G delta set. See that G is the open G, that is the symbol there is G delta set if. Now the G is for open, as I said, is the first letter of the German word for open, and the symbol delta is used for intersections and the symbol sigma is always used for unions. Okay. So G delta, that means G delta intersection of open set, but only countable. All these are countable. If it is a countable intersection of open sets. So now we got some more things in my basket. I had open intervals and then I did some constructions, I grew and then I got more products, they were the open sets. Then now use these open sets to grow more products, they are the G delta sets. Now can I now, so the G delta sets include all these things, even open sets will be called G delta sets, because every open set is intersection with itself, is a finite intersection of two open sets. Or you take, if you have an open set A, I can write it as A intersection phi intersection phi intersection phi intersection phi. So it's a countable intersection of open set. So every open set is also G delta, but there could be different other things also. So the G delta is a bigger basket. I had a small basket. Now a bigger basket which included all this and more, namely open sets. Now I have a bigger basket which are called G deltas, which include some new things together with the old already what I had, namely the open sets. Okay. Now can I build more from this? So again when I build, can I start again? Take this bigger basket and try union. Take randomly fellows from this bigger basket and put union, you will get something new. So union of a countable number of G delta. Okay, so what is G delta sigma then? So G delta, I start with G delta and then do it as a sigma. Okay, this is the set of all, the collection of all countable unions of G delta. Is there another class here after this? There are some students waiting, that's why. Now you can see I had open sets, open intervals, I produce one thesis, namely open set construction. Then I produce another thesis which is called the G delta construction. Then from there I produce other G delta sigma thesis. Now I can produce infinite thesis. I can take G delta sigma delta. G delta sigma sigma will not give you anything. Again it will be G delta sigma only. But I can do G delta sigma delta sigma delta sigma delta sigma. So I am in business for the rest of the thing. Continue this. So you get a whole variety of sets on the real line. We look at these things from a different angle. Okay. So this is what I think. This is basically a construction. These constructions are due to a mathematician called Bayer, who has done many such constructions in mathematics, and there are some very important theorems named after him, Bayer's theorem. Okay. Now why not I do the same thing starting with closed sets? Okay. So I have the closed sets. Now if I do delta, I won't get anything, right? Because intersection of closed sets is closed set. So if I did G with delta, I do F with sigma, and then a delta, then a sigma, and this can go on. Okay, there's another line of, this is the dual construction. Whatever I did there, do the dual construction there. So there are these are some very big families of important sets. Many theorems can be proved using these sets. Okay, many of the classical analysis theorems can be broken down as theorems in this by breaking down the basic set involved where you are studying into such small sets. Okay, that's old classical proofs. Okay, now I don't know whether I also did this in the last part of the previous course. Now I am going to look at some other construction which is slightly different. At the moment, to begin with, I don't what do I say? I don't look at any topology. I'll bring in the topological aspects a little later. Suppose this is probably what I am doing in the beginning. I can do without any real line, without any topology, and an arbitrary set. Okay, and this is what we use in measure theoretic constructions. Okay, so suppose I have a set omega, any non-empty set. Okay, and I am not interested, of course, I may or may not be interested in all the subsets of omega. Okay, I may be interested only in certain subsets of omega. So let us say B is a collection of subsets of omega. May not be, may or may not be all subsets of omega. In other words, it may not be 2 to the power of omega, but it may be 2 to the power of omega or something smaller than 2 to the power of omega. Whenever I take such a collection, I want this collection to be self-contained. I want to look at self-contained collections. So what do I mean by self-contained collections? Well, after all, I am dealing sets. The only thing I can do with sets are the set theoretic operations. So when I say self-contained, what I mean is if I take the sets in this collection and I do any set theoretic operation, the resulting set must also be in this collection. I don't have to go outside this collection. So I want B to be self-contained. That is, it must be closed with respect to all standard set theoretic operations. What do I mean? I can take a set in that collection and look at its dual, conjugate, complement, that must also be in that collection. I can take certain fellows from B, put a union, that must be there. Put the intersection, that must be there. Well, when I say, whenever I talk about union and intersection, I will allow up to countably infinite. Beyond that, I don't want to get into complications beyond that. Okay. So it must be closed under complementation, it must be closed under countable union, it must be closed under countable intersection, it must be closed under set theoretic difference. If I take a set and pull out a portion of that from another set B, the remaining must also be there, and so on and so forth. All the set theoretic operations, the standard ones are complementation, intersection, countable intersection, countable union, set theoretic difference, symmetric difference, and so on. Okay. That is one. So of course, I assume this collection to be non-empty collection. There is at least some sets that are some subsets of omega it. One, if A is in B, A complement is B, must also be in. That is, if it is closed under complementary. If somebody is there, his dual must also be there. 2, Aj, J equal to 1, 2, a sequence belongs to B implies union J equal to 1, 2, etc. Aj must also be B, and intersection J equal to 1, 2, etc. Aj must also be in B. So I can do countable unions and countable intersections, still the result will also be, it's like what we define as a subspace. If I take any two vectors, that sum must also be there. If I multiply it by a constant, that must also be there. So there what we are doing is this vector space operations, addition and scalar multiplication. Here I have sets, only set theoretic operations I can. And the third is, if A1, A2 are in this collection, the set theoretic difference must also be in that collection. And finally, if A1, A2 are in B, this is the notation, this is called the symmetric difference, A1 delta A2, which is A1 minus A2 union A2 minus A2. That must also be in. And this is obvious from this and this, okay, because this portion is there, that portion is there, and union must be there. Okay, so that is what I mean by self-contained. I say that a collection of sets is self-contained if I can do all the standard set theoretic operations for them without having to go out of that set. Right, such a thing is called a sigma algebra. B is called sigma algebra of subsets of. We will redefine this slightly because some of these requirements are redundant. I said that this will follow immediately from this and this, so I need not state that. Similarly, I need not state this also, and I need not state this also. If I have this and this, all the other things will follow, and that's how we will give a definition of a. So, sigma algebra is nothing but a collection of subjects, which is a reasonable collection, which gives you, has enough space for you to do all the things that you want to do. That's all. intuitively. That's what we mean about subspace is a reasonable space where you want to do all the vector space thing within, you don't have to go outside. That idea will keep coming again and again. Now, if you look at, take for example, O, the collection of all open sets in R. That is obviously not a sigma algebra, because if I take an open set, its complement may not be open. If it's a closed set, it may not. It will be a different set. So obviously, it's gone. Okay. So O is not a sigma algebra. I'm sorry. What did I call sigma algebra? Of subsets of R. Okay. Of subsets of R. So again, you look at the analogy in the vector spaces, which everybody more or less is familiar, because everybody knows a little bit of linear algebra. So if you have a collection of vectors, it may not be a subspace, okay, but then you want to embed it in a subspace. That is what you call as a subspace spanned by. So when you embed, you want to do it optimally. You want the smallest subspace in which you can put all these vectors. So since this is not a sigma algebra, I want to embed it in a sigma algebra, and I want to do it optimally. I want the smallest sigma algebra that will contain this, and that is called the Borel sigma algebra, and anything in that sigma algebra is called a Borel set. Okay. So can we embed O in a sigma algebra of subsets of R, and can we do it optimally? So more generally, let omega be any non-empty set, and be a non-empty, okay, let's call it as be a non-empty collection of subsets of omega. Can we find, question 1, can we find a sigma algebra, let me call it a sigma, of subsets of omega such that B is contained in omega sigma? I have embedded it in a sigma algebra. 2, can we do this optimally? What do I mean? This must be as small as possible. Okay, that must be as small as possible. The first question is easy. Take all subsets of omega, that is 2 to the omega, that is a sigma algebra, because everything is there. So whatever you do, it will also be there. So there is already a huge sigma algebra which is encompassing everything. This is exactly analogous to the vector space case. Given any collection of vectors, is there a subspace that contains them? Yes, the whole space is definitely a subspace which contains all of them. The entire vector space is something, it's a subspace which contains them. But that's not a big deal. What we want to do is, as optimally as possible. What is the smallest subspace that contains them? And that is what is called the subspace generated by the given set of vectors. So subspace spanned by the given set of vectors. Analogously, we will find the answer to this question is yes. Okay, and that is called the sigma algebra generated by B. Okay. Now I will do this next class, but let us look at some very trivial situation. Suppose B is itself a sigma algebra, then what will be the sigma? Itself, because if you have already a subspace, the smallest subspace that contains is itself. Similarly, I already have a sigma algebra. Why do I need anything bigger to embed it? You already have embedded it in a sigma algebra. So if B is a sigma algebra, no work to be done. He is himself the Sigmaalgebra that contains him. The question therefore is, B is not a Sigmaalgebra, how do I go about doing it? Okay. Now, you will see that how do we do it in vector spaces? It's worth seeing because this construction is common in many places. The same idea is used in several areas, okay. The smallest embedding into a standard material. The standard formatting is a Sigmaalgebra. Here, the standard formatting is a subspace in vector spaces. The standard formatting is a subgroup in the theory of group. The standard formatting is a subring in the theory of rings. The standard formatting is a subfield in the theory of fields. So that standard format, and the proofs are the same. How do you put it in a standard formatting? And the proof is essentially the same in all the cases. The idea is the same. Okay. How do we do it in vector space? Let's just review that and then I will continue in the next class. Suppose I give you a vector space V. This I will do again next time, so don't worry. So we'll just look at this Sigmaalgebra parts of. I think this is the whiteboard pen. Suppose I have vector space V, and I have a small collection of set of vectors inside that. Okay, and that is now I want this may not be a subspace. I want to embed it in a subspace and I want to do it after. What is the construction of the vector space? If S were a finite set of vectors, I will take all the linear combinations. And the other idea is therefore you take all, suppose if S is infinite, it is the set of all finite linear combinations of this and that works, okay. But another way of looking at it is, take all possible subspaces that will contain S. Okay. Do I know at least one of them? Yes, V. V is one subspace which contains S. So therefore, the collection of the subspaces which contain S is non-empty. Now take the intersection of all the subspaces which contain S. That will also be a subspace. And that will be the smallest subspace and S will belong to that. This is the simplest argument, okay. If you have a small world, you want to put them in boxes, take the intersection of all the sizes of all the boxes and you get the smallest size box, and since this fellow belongs to all the boxes, he will also belong to the intersection. That is the simple common sense argument. The same argument will work here also. The things that we will have to prove will be, is there at least one Sigmaalgebra contains B? Yes, 2 to the power of omega is one Sigmaalgebra that contains. Now therefore take the collection of all Sigmaalgebras that contains B, take their intersection, and what we have to show is the intersection of any collection of Sigmaalgebras is also a Sigmaalgebra. If we show that, we are done, same proof. So the proof in vector spaces will be the intersection of any collection of subspace is subspace. Here will be the intersection of any collection of Sigmaalgebra. In group theory, it will be the intersection of any collection of groups is subgroup. Intersection of any collection of subrings is a subring. Intercollection of any collection of subfields will be a subfield. Idea is the same, okay. And everywhere you will get the correct optimal embedding, okay. So next time I will do this process and prove that the intersection of any collection of Sigmaalgebras is a Sigmaalgebra. Then the idea is, I have O, it is not a Sigmaalgebra, so I must be able to put it in a Sigmaalgebra and I can put it optimally, therefore there is an optimal Sigmaalgebra that contains O, okay. The optimal Sigmaalgebra that contains O is called the Borel Sigmaalgebra. Anybody who is inside that is called a Borel set, okay. This is what Borel did. And look at this, that fellow puts everything together. Because all open sets will be there, their complement, all closed sets will be there. So all the constructions we did, Gdelta, sigma, F delta, F, all of them will be put inside that. So that is one big thing which encompasses all your construction, this Borel sets. It's a very important collection of subsets in the, when you study probability theory, random variables, real valued random variables. We somehow say the F inverse of a Borel set must be an event for whatever reasons, okay. Why the definition comes, that we will see later, okay. So, so that's the first thing that I will do next time, and connect these two and introduce the notion of a Borel set, okay. I think is the right time to stop. This time I may not be very good in sending lectures.